participants tells you that you are offering a great thing here. Thank you so much. So now I will go. It had worked before. So, okay. Chris gave you the title, and I'm actually a bit nervous about the whole thing here because I felt I'm not in this community very much, and maybe off with my topic here. And when you are nervous, you start to add things on, yeah, in the hope that something on my carpet, yeah, the pearls or the other gifts, yeah, are interesting for you. So I added here laboratory experiments to the field experiments, and that's actually what I will start. And you can bet this is not my work alone at all. So from my place here, it's Jen and Max who contributed the most, and to some of the numerical stuff, the people from Stuttgart, Patrick and Holger, and the whole STIMTEC team, and I will give you the names later on the slide. Yeah. Yeah. I mean, why do I think?
Sorry to interrupt. It's Chris. The little floating window that you see that starts with me.
I'm sorry.
Yeah, perfect.
Now it's gone. Yeah.
Yeah. Otherwise,
thanks for telling me.
Beautiful. Thank you.
Okay. So what could this hydromechanics business of fractures? How could that be of interest to people working on earthquakes? Yeah. I think it does, and it becomes pretty prominent, at least when you think about induced seismicity. And here, like in a nutshell, induced seismicity and its relation to fluid injection, right? I mean, very simplistically here, a borehole. Do you actually see my mouse when I move that?
Yes, it's small, but we see it.
Okay. So in the sketch, you have this borehole stress state, and these blue things indicate the penetrating fluid with decreasing pressure away from the borehole. And one concept here of induced seismicity is that if there are pre-existing fault zones, fractures, or whatever, as you all know, that the increasing fluid pressure on that reduces the normal stress, yeah, and by that you can reach the failure limit of that particular fault zone. And in a simple sketch, that this means moving the Mohr circle, yeah, towards the origin, and maybe eventually it hits the failure criterion, right? For me, this is all fine, but there seems to be aspects missing. Yeah, there's one thing that we restrict mostly to a diffusion treatment of the pressure change with time and distance. Yeah, and I think we have to respect the coupling between fluid flow and deformation. Yeah, this whole business is very stress concentrated, yeah, stress focused, and probably the deformation part is missing to some extent, yeah. And what we actually don't know too well, yeah, is the distribution of the pressure in deforming fractures or fractured medias as a consequence of this neglect of the coupling, right? So that's kind of what's driving me, yeah. And yeah, in a way, you could say it's much ado about nothing, and also a narrative, and that's what you are up for in the next 45 minutes or so. Yeah? One thing that it's not really bothering me, but our common wording implies that fractures are mechanical bodies, right? But that's not true. Yeah, I mean, fracture refers to the absence of solid material. And if you look back into Mechanics 1, yeah, the first page, it says mechanics is about physical bodies, right? Okay, so we are actually dealing with the voids in solid materials, yeah, and what is deforming is not the fracture, but it's the solid that is kind of housing this void, right? And to this deformation, there are two aspects, and there's a nice sketch here in this paper by Murdoch and Germanovic that, to my knowledge, for the first time kind of visualized that nicely. There are two aspects that control the deformation of fractures. It's the contacts, if there are any, between the opposing surfaces. But there's also another contribution, which is something that you might want to call geometrical stiffness. Oh, I'm sorry, this should be not filed, but field, because the talk today, when it is about lab studies, it's mostly contact mechanics, but we get to the geometrical stiffness when I move on to the field studies, right? And lab people might be very much aware also of this geometrical stiffness from the works of Kachanov. I don't know how to pronounce that correctly, and his co-workers. And he phrased it nicely here, that the stresses that are applied to such a void are counteracted by two factors, the cavity stiffness, yeah, and the fluid pressure is something is in there. And when Kachanov talks about this cavity stiffness, he means the geometrical stiffness. There are no contacts in that crack theory, and in this compliance tensor that is central to this work. Yeah, you only find mechanical properties of the solid, because the crack doesn't really have mechanical properties, even though at the end we assign stiffness is normal or tangential to it, but their origin lies in the nu and the E, so the Young's modulus and the Poisson's ratio of the solid material. Okay, and a bit on my terminology, which I will hopefully follow somewhat through this talk. This is simplistic, but in a way people are not strict with it, probably me neither. Yeah, this is supposed to be a cross-section, a series of cross-sections through fractures, and this is a plane view, plane in the sense that a fracture is more or less plane, right? Okay, and I distinguish mechanically and hydraulically open or closed. Okay, this guy here is mechanically open because there's no contact between solids anywhere, as you also seen in the plane view. And naturally, it's also hydraulically open. Yeah, okay. And for me, the criterion for hydraulically open is at least in one direction you have a through-going path allowing for fluid flow. Okay, mechanically closed. That is the state when solid is in contact somewhere. So for example, here at this contact, and then in the plane view, you have a contact area. Yeah, and this, yeah, might be a different fracture or the same fracture under higher normal stress, and the contact area increases, but you still find through-going paths here, actually in the both mutually perpendicular directions here. So it's still hydraulically open. But eventually, you might reach a state where the contact area percolates, yeah, in the plane, and then it's hydraulically closed because there's no fluid flow possible in any of the directions. But this does not mean it's mechanically inactive, because there are still voids there that might affect your deformation behavior. Yeah. And here in this kind of introduction or glossary, a bit more, I think most of us are familiar with that. If such a interface here with these rough surfaces, yeah, is under a far field stress, that the contacts that are formed between these two surfaces actually might experience much higher local contact forces, and that might vary quite a bit along that fracture, and that they might not all be normal actually, but they might be normal, tangential, whatever to the contact plane. Yeah, and because we will talk about the deformation of fractures, we have to kind of find a way to describe that. And at least in lab, what we do is, we monitor a change of an effective mechanical aperture. So we, in the two opposing blocks, we have reference points, and then a load is applied or something, and we measure the distance of these reference points and call that kind of the change in mechanical aperture, this distance by which the reference points move. That's the best actually we can do in a mechanical sense. And something that people sometimes, it's at least my experience, are not so aware of, that for fluids in the fracture, something very similar to the contact stresses applies too. That the fluid pressure does not have to be constant along the fracture. And in that respect, the balance of the stresses is not by any means as uniform as that, because here you would need in this failure criterion, you need some kind of an average fluid pressure or something, right? You have to integrate over the whole interface here, whatever your complicated PF of X might be, to use it in this relation. So there's a difference between the local and the mean local fluid pressure, and that actually affects our failure criterion. But what is even true too is that local pressure deforms the entire fracture. So if I have a high pressure here somewhere in the center of this fracture, because there's an inlet or whatever, it moves up, or it moves the two parts away from each other everywhere. And that is something we sometimes tend to forget, that the deformation can be quite complicated ways be related to this distribution of the pressure. Okay, and there's how do I do this? There's a prominent example that we also worked on, but we're definitely not the only ones. That is inverse pressure response, and borehole testing. So here's borehole 1, which is the injection borehole, and it is connected to a second borehole, a monitoring borehole. Both are intersected by a fracture, and you have a certain injection protocol here for your injection borehole, flow rate in, no pumping, flow rate out, and so on, And these are the pressures that you get from this injection protocol. The blue one is in the injection borehole, and this reddish one is in the monitoring borehole. And funnily enough, you have an increase in the pressure in the injection borehole, but anytime it increases, the monitoring borehole pressure first decreases, and vice versa. So it works in either direction, whether you increase or decrease the pressure in the pumping ball. And that's exactly this effect. You pump in here, these two surfaces separate, and so what happens, you have a dilation back away here from the injection point, and the pressure decreases. Okay, so sorry, these are the points I wanted to. And before I can really start, I also want to give a brief review here of the most important fracture properties that I will use today. And one is the stiffness, which is hopefully consistently kappa in the slides. It's the change in effective mechanical aperture, with change in far field stress. And transmissivity, which is something like it's a hydraulic property, and it's related to permeability that you all know from porous media. And we also at times say that a fracture has a permeability, though this wording in itself is already a bit complicated. It has its origin in this famous formula for slits, which would be fully open fractures in a way with smooth surfaces. And then this permeability of a slit is the aperture squared divided by 12. In borehole testing, I usually do not know the delta at all, but I need the delta because it's also the height of the entrance. So this H in this transmissivity equation, yeah? And so the borehole people lump everything into one number, which is transmissivity. It's proportional to permeability, but also the height of the inlet, and then fluid properties, rho and eta, which is gravity, density of the fluid, and viscosity and fluid, and gravitational acceleration. Transmissibility is somewhat simpler, but not as often used, yeah, which is then just the HK, which for a fracture would be, for a slit, would be delta cubed divided by 12, and that's the origin of, or that's the expression of this law that many of you will know, the cubic law. Yeah, and if you want to transfer things, yeah, later on my slides I will use transmissivity. Yeah, you have to multiply them by 10 to the power 7, and then it'll be something like this cubic law if you want to. But I'll come back to that maybe. A brief overview now of this, what is coming. Yeah, I start with the lab. Yeah, and you a keyword there would be test of the cubic law. The good thing is we can look at static or slipping fractures. And then in the field, yeah, a note here, anything we do, we rely on the validity of the cubic law, but only locally, yeah. And then in the field, we look at closing and opening fractures from the STIMTEC experiments. One is an analytical study, one is a numerical study, and they refer to different fracture geometries, which I will explain later on, axial and radial, and one allows for leak-off and the other does not allow for leak-off. That's kind of the table of contents in a weird way, and probably it doesn't help, but anyway, so you will see 3 parts, laboratory, and then 2 parts, field study. Okay, so let's start with the laboratory experiments, which Max Gebel performed mostly. And we used a granite, a Padang granite, probably poorly pronounced, it's from China, and introduced model fractures into that. And in the first set of experiments, it's essentially 2 cylindrical plugs on top of each other, yeah, and they have this interface, and we prepared these surfaces just as saw cuts, or we ground them with different grids, or we polished them. And the upper plug has a central borehole, yeah, through which we can inject fluid into this fracture, yeah, to this model fracture. We can apply axial stress to this assembly, confining pressure, and we measure the axial deformation and also the flow rate into this borehole. And specifically, the fluid pressure in this borehole, and thus in the pressure in the fracture, is varied in a periodic way, actually a harmonic way. Yeah, this is kind of our old lady, the green Rick or green Bertha. I think it was built in the 1970s, way before my time at all, but it's still doing its job pretty nicely. That is the pressure vessel in which this sample is housed, the confining pressure, and so on. Yeah, and I'm more than happy to give you more details, but probably you're not so curious about that. How do we use this to estimate the hydraulic properties of this fracture? Yeah, I mean the stiffness we just get from the stress and it changes, and from the axial deformation and it changes. But how do we know something about the hydraulic properties of this fracture? It's by the help of this harmonic oscillation in the fluid pressure, which would be here, this blue curve, yeah, and it would be going on and on and on, yeah. And at the same time, we can measure the flow rate that is going into this borehole and thus into the fracture, which is this green curve. And these 2 curves allow us to calculate two parameters. One is the amplitude ratio, yeah, and the other one is the phase shift. And these two parameters allow us to determine the two hydraulic parameters we are interested in. One is the transmissivity, the transport aspect, and the other one is the storativity, which is the storage aspect of the hydraulics in the fracture. And first a bit on this normal stiffness. Yeah, these diagrams are busy, but what you see here is the change in the mechanical aperture. Yeah, we cannot measure absolute aperture, only the changes. Yeah, and the stresses. And these are a bit funny because we did them at different confining pressures. That is this sigma n effective, and then at a given confining pressure, we applied a deviatoric stress on top of that. So the confining pressures kind of give us the deformation, the base deformation, this dotted line, and then the deviatoric load gives us these lines that kind of branch off from that. That is the first important observation. Yeah, the stress path matters for stiffness. That makes it pretty complicated physical property. And the second aspect here of this diagram is we can measure only differences. Yeah, so the black lines are, start with the red ones. The red ones are the intact rock. So before we split the two plugs, we measured them as an intact rock, yeah, and then cut them in two pieces and so on. And the black is the rock and the fracture. And you see the delta, the deformation is larger, and the difference is only what we can ascribe to the fracture alone, yeah, to the contacts that make the fracture, yeah. So it's actually the blue curves that we are after, yeah. And therefore, here in this diagram on the side, the fracture normal stiffness in Pascal per meter, kappa n, yeah, is measured only for these blue curves, because that's the deformation that is solely due to the fracture, yeah. And again, you see this two trends here, one for the confining pressure and then the other one for the deviatoric loading. So it's the stress path matters, and obviously the stiffness increases with normal stress. Yeah, we are definitely not the first to realize the second part, the dependence on normal stress. Yeah, it's probably due to the increase in local contact areas. At least if you use a simple model like Hertz and contacts, yeah, that's what it's going to tell you. For such a contact between two spheres, yeah, the contact radius increases with load, the normal displacement increases with load, the contact stress increases with load, and the normal stiffness here increases with load. And I added that here to give you a feeling here. So my particular example is for spheres with a centimeter diameter. They have contact radii that are much, much smaller. You see here a quarter of a millimeter, say at 40 Newton. Yeah, the stresses are in the range that we are used to for far field stresses, 100 megapascal. Yeah, and the stiffness is 10 to the minus 7 Pascal meter. Yeah, so, and here we had, oh, actually, I'm sorry, I cut that off. This is a nightmare. This is kappa n times 10 to the 12 Pascal meter. So these are about 10 to the 11 Pascal meter. Yeah, so much stiffer than this individual sphere contact. What about? And this is a collection of all the data that Max assembled here. The colors are for polished surfaces, and here these two grids, so increasing roughness. It's all this stress range up to, say, about 100 megapascal. And they range here from like 10 to the 8 to 10 to the 13 Pascal per meter. That is also problematic. I mean, are you aware of any other mechanical property that covers that many ranges? I mean, people in exploration geophysics are used to huge ranges in resistivity, for example, or electrical conductivity. But in mechanical properties, to have a several orders of magnitudes, that is unusual. Yeah, there's a very famous study here by Parek Nolte from 2000 or so. We are in a similar range here. Maybe she's a bit higher in some way. And then there's a collection. Yeah, don't worry about this intermediate ones for a second. Collection by Zangerl, and the good thing here is he also collected the few data that in situ studies provided on this properties, fracture stiffness, and also some laboratory studies. And I mean, the message is the same, right? And you could say, okay, a typical value is 10 to the 11 Pascal per meter, maybe. Yeah, if you go back to Hertz mechanics, then what does that mean? To get 10 to the 11, you need 10,000 contacts, yeah, with curvature r equals 1 centimeter. Or you need 100 contacts with curvature 1 meter, just to get an idea, yeah, of what that means, yeah. Okay, so what controls normal stiffness? Yeah, definitely normal stress. We saw that. At given area, roughness plays a role. But then we were wondering, can we say something about, I mean, why is it that field data and lab data give kind of the same range? Yeah, that for many mechanical properties, that's not true, right? I mean, field is different than the lab. And here Max collected the stiffnesses color-coded now. Yeah, our beloved 10 to the 11 would be here some bluish thing. Yeah, and try to get the fracture areas from the various studies, yeah, and plotted them as a function of area, because we wanted to see is there some trend here, yeah, does it go up or down with fracture area? And if you look at a certain value here, like this light blue ones, yeah, it could go up, yeah, or the greenish ones maybe could go down with area, maybe the greenish ones, but it's not consistent. Yeah, here it splits off. And if we go to the higher stiffnesses, yeah, then it would rather, I mean, the very few data you have, what trend do you want to make here? But it seems like it would go rather up. So I don't know. To me, it seems like there is some scaling here, which keeps stiffness more or less scale independent. And to me, it has to do something between the rate and the wavelength of the roughness and the size. Maybe that's what people also see in the Hurst exponents when they look into fractures and so on. That's something one had to investigate more. Yeah. And this is like a page from the New York telephone book, right? I mean, inaccessible, I'm sorry for that, but it's a collection of the hydraulic properties, yeah? And I have to emphasize, our technique assumes that simple pressure diffusion works, yeah? So no coupling, no nothing. So there are kind of effective properties. If there was an equivalent medium that obeys pure pressure diffusion, then the hydraulic properties would be like that. And it's the top row is transmissivity in square meter per second, yeah, 10 to the minus 12, yeah. That would give you a fracture, an effective hydraulic width of 10 to the minus 19, 10 to the minus 18, of 10 to the minus 6 meter, very small. Yeah, this is the storativity is unitless. Yeah, that is the storage parameter, and that's their ratio. T and S give you the hydraulic diffusivity, which is in square meter per second, and that is actually the parameter that people like Shapiro and so use to deduce from the growth of seismic clouds. Yeah, they assume that the seismic cloud grows essentially diffusion controlled, and then the distance and the timing, yeah, gives you this hydraulic diffusivity. Okay, and the individual plot is given as a function of normal stress now in a logarithmic way to have a double logarithmic diagram. And you see that the hydraulic properties go down with increasing normal stiffness dramatically, yeah, like here, 2 orders of magnitude for the less than 100 MPa stress, yeah. And again, the color coding here is we have to compare things, yeah. The black one is the intact rock. It's not fully impermeable, yeah, so there's more than just the fracture, and the colored ones here are polished and 2 different roughnesses, and you see that the rougher the interfaces, the higher the transmissivity. Okay, and interestingly enough is that the diffusivity itself is much less stress sensitive. So somehow these 2 cancel each other, these 2 effects. The transmissivity goes down, but at the same time, the storage potential also goes down, and that keeps the diffusivity constant. And something that makes this a bit troublesome is that if we do these tests at different periods, yeah, you remember we sinusoidally vary the pore pressure, yeah, and if we change the period, yeah, from fast 1 second to long 100 seconds, the answer we get from diffusion theory changes. That should not be the case. Yeah, if diffusion theory would be correct, then we should get the same answer for all periods. Yeah, this is telling you something. Yeah, that there is coupling and actually nonlinear coupling involved here. Yeah, that causes this trend with T. What is the immediate implication? This affects the period affects the pressure distribution in the fracture. The longer we go, the more the excitation from the borehole penetrates into the fracture. So it affects actually the effective mean stress, yeah, when I go longer. And these are kind of shifted essentially along the stress axis in a way, yeah. Anyway, so we can measure it, and the no news, yeah, the transmissivity of a fracture is higher than of intact material, and substantially. Yeah? This is a kind of a summary of these diagrams. Again, we have this aspect that the hydrostatic data, these are the squares, yeah, and the ones collected then at deviatoric loading, that are the lines here, they are not on top of each other, yeah. So we have kind of the same stress path dependence as for compliance, yeah, or stiffness. And you can try to see whether our data are in agreement with the cubic law. Yeah, the changes in the mechanical aperture had to be related to the changes in the transmissivity, and they should plot on this line. Yeah, and they don't. You can cure that and just say, okay, the mechanical aperture is not the right aperture. You have to know the hydraulic aperture, and then the cat bites its tail, because the only way I can determine the hydraulic aperture is by assuming that delta T obeys the cubic law, and I have to take the third root of that, and then sure enough it plots on here. Yeah, but assuming that this really gives you a measure of how the fracture is tightening, yeah, and the space is getting closer, then the cubic law does not hold for the model fractures. And I'm not so surprised that it doesn't do, because it has the surface separation in it, but it also has contribution by the change in the in-plane percolation. Yeah, you remember the contact areas that I tried to sketch, and if that changes the flow, yeah, it has to is less straight more and more. That will affect that too. Okay, and that probably more interesting for you, what happens during sliding, during frictional sliding. Yes, so we tested a few rocks here now with a saw cut, with polished and so on. Yeah, but with an inclination to the cylinder axis, but everything else the same. Yeah, our inlet borehole, we oscillate and so on. And I think this particular diagram is again for Padang, and these are just typical friction curves, right? Axial strain and differential stress. Yeah, you apply stress on this one, you monitor this, the slip, and these are done at 4 different confining pressures. So it gives you a friction coefficient of say 0.6 or something. Yeah, very typical. It's very reproducible. Yeah, these 2 curves are always for 2 different samples. And you also see maybe this wiggling. This is not because our machine is so poor, but the wiggling comes from the oscillation of the pore pressure. Yeah, that couples back into the stress. Yeah? Okay, and now let's have a look at the one experiment at 60 MPa in somewhat more detail. Here you see again the loading curve, yeah, differential stress, and this time as slip distance. Yeah, so we can apply a few millimeters on our saw cut samples here. Yeah, and then have steady state. Yeah, nice steady state frictional sliding here. Okay. Yeah, first the loading part, and then steady state, and then a little bit of relaxation when we stop the machine. And the blue curve is again the transmissivity, 10 to the minus 12 here. And it goes like this. Yeah, first observation, it covers half an order of magnitude from its highest value at the start to its lowest value it reaches during the sliding. Yeah, actually, that is not what people typically think. And there's a nice study by Julian Mecklenburg and Ernie Rutter that came out recently, and they made the same observation. Yeah, contrary to what people think, and that comes from very low stresses in engineering geology, actually. Yeah, it seems like that the transmissivity, or the permeability, if you want, so does not go up with sliding. Yeah, first it goes down, and why does it go down? Because the normal stress increases quite a bit, and during the sliding, I mean, if you want to, you could see a little trend here that it goes up. Yeah, after quite some sliding, but first it goes down, and the variation here is much smaller than the variation here, the going down with the increasing normal load. And I have this kind of little cartoon here to emphasize phases. So going down very early on, then for some reason it goes up, and this is reproducible. We saw that in like 20 experiments. Whatever we did, we have this little increase here, and you see also the slope of the loading curve changed a bit. So something is happening. Whatever, I don't know. Yeah, then it continues to decrease until you reach this kind of steady state regime where also the transmissivity seems more or less steady. But for these wiggles here, and these wiggles are real. Yeah, they actually reflect pressure pulses. Yeah, our mean pressure jumps up and down by a little bit, yeah, during the sliding. And I think what happens is like that you have like compartments of fluids on this fracture plane, yeah, that are at different pressures. And when you slide them, yeah, they kind of connect, which could lead to an increase in pressure, or they, if a high pressure one connects with a low pressure one, it could lead to a decrease. Yeah, and we can monitor that actually in the amplitudes of these wiggles here, and we see that the coupling evolves too. But I thought that would be overdoing it. if I show you that too. And at the very end, that's also interesting. When the stress relaxes a little bit, so kind of after the earthquake, yeah, we have a substantial increase in transmissivity, yeah, more than all the change, yeah, during the sliding. Yeah, I found that interesting too. Okay, this is again one of these collections: transmissivity, normal stress. The squares are the hydrostatic experiments, and the lines are these deviatoric ones. They are not exactly on here because they're different samples, so they have sometimes slightly different starting values, and we didn't want to cheat here, so we left it. But you see that these lines do not follow the simple relation, yeah, constrained by the hydrostatic experiments alone. Okay, so that was the cheating part with the lab not in the title before, and finally I make it to STIMTEC, and hopefully I'm not overdoing it here time-wise. STIMTEC, I promised you showing you the people, and maybe now you understand why I didn't put it on the first slide. We are quite a bunch, the STIMTEC team, a wonderful cooperation here between company, Geomecon, the people from GFZ, and the people from Freiberg, yeah, and the money comes from the federal minister for education and research. Yeah, and we had three external partners, companies here, Solexpert and Gemuk and the LIAG from Hanover, that helped us doing this experiment. And we are actually very happy that STIMTEC got extended to STIMTEC X, and we have another year and a half or so to go. The experiments are taking place in a beautiful old mine, silver mine, that's been active for almost 1,000 years. Unbelievable. Yeah, it is the tunnel we are working at is about 110 to 130 meter deep. The rock that is penetrated there is an anisotropic gneiss with damage zones and joints and all sorts of things. Yeah, and I think I should move on here. There are two tunnels, two more or less parallel tunnels. Yeah, and that is the benefit of such a mine experiment, right? We have an injection borehole and almost 20 boreholes around for monitoring purposes, yeah, with acoustic emission sensors, with accelerometer sensors, hydraulic sensors, and so on, yeah, a situation that you would never have in situ, okay? But I will not report on acoustic emissions here, sorry guys. I will stick here with my theme, hydromechanics, and I will report on results of injection experiments in intervals, yeah, in this injection ball. And an interval means that we use such a double packer probe, yeah, to isolate a section of this interval, of this borehole, yeah, roughly 1 meter long, and the pressure or the fluid we inject, yeah, pressurizes only this section, not the entire borehole. That allows us to do repeated tests, yeah, at a total of 10 depths actually, and compare these results. Yeah. At these 10 intervals, we followed a certain scheme, yeah, to make them comparable. Here I show you an example for one at 24.6 meters. After an initial injection, yeah, this is volume on a logarithmic scale and pressure measured in the interval, where you check for the tightness of the interval. We inject until we reach breakdown, it's called, yeah, where the pressure increases, you pump, and eventually something breaks, yeah, and the pressure goes down. You continue injecting some fluid, the pressure declines further maybe, yeah. Then you shut off the pump, initiate a so-called shut-in phase. repeat injection several times until you have more or less a constant pressure. Yeah. And after that, we did a so-called step rate test where the injection rate was increased in steps and the pressure response in steps, yeah, from low pressures to pressures similar to these refract pressures. And then after that, we did also this periodic pumping test as the ones that we did in the laboratory. With the difference, these are not really harmonic, but they are simple periodic. Okay, and in the two studies I show you now, yeah, we'll focus on the shut-in phases and the step rate test phase. But before doing so, I wanted to show you these are impressions from these 10 intervals after the fracking operation. And the black lines you see here are the fracture traces that were created due to this breakdown, the failure of the borehole section. And I don't want to go in describing them in detail. I think what you can immediately see that it is quite variable. Yeah, that the 10 intervals show quite different fracture traces. Okay, and how do we deal with these data? Yeah, now we have to go beyond diffusion analysis, and still we need simplifications. We make a single fracture assumption. Yeah, so we think that there's only one fracture responsible for the response, and we can select between two geometries for the fracture, two simple geometries, truly radial, so the borehole would be here, and it's a radial fracture around the borehole, or axial, like indicated here, the blue again, the borehole. And we evaluate the mass balance and the momentum balance for the single fracture, but in a fully, everything accounted for, and that gives you a pretty complicated partial differential equation. Yeah? And the first part is what you might know from diffusion, but now the aperture is not lumped into hydraulic diffusivity and before the Laplace, but it's still in one derivative. Yes, because the aperture may change, right, due to the change in fluid pressure. The nozzling effect, that is accounting for the geometry change of the fracture, along its lateral extent. A quadratic term, always a nightmare when solving differential equations. And now, other than in the diffusion equation, we have a non-zero right-hand side, which is the coupling with the deformation of the solid. Again, here the delta, twice, the aperture, and how it changes with time. Yeah, that makes the coupling. Okay, and so in addition to this equation for the fracture, you have to solve in parallel a second equation that for all the rock around this fracture. Yeah, we do this typically with Biot's theory for porous media, but there are other approaches. Not given here in this one, you could have another term here on the right-hand side, a source term for leak-off. What do I mean by leak-off? It's the fluid penetration from the fracture into the matrix if it's porous, right? And again here, the amount of leak-off depends on the fracture, on the pressure distribution in the fracture. Okay, so Jan's work is on these shut-in phases, yeah, and she went for axial fractures because that gives you a 1D formulation, yeah, and for these fractures, she employed a nonlinear contact mechanics formulation. Some people know this as Barton's law, which is a good description of what we saw in the lab, what I showed you before. And now aperture, sorry, this moved, is still, it's not h of t, but it's delta of t. So that's the simple the simple 1D formulation. And one thing that was very important to realize here, that this experiment involves actually 3 hydraulic storage containers. The borehole, yeah, which has a fixed storage capacity, you can measure that. the fracture, which has a variable storage capacity because it can balloon, it can open and close, yeah, and the matrix around the fracture, which is the worst storage container. It's just infinite, right? I mean, it's an open container. Whatever it gets, it takes, right? So there's no limit to that. And here's an example of such a shut-in phase. Now, interval pressure as a function of time. This is one of these refrac cycles that stops, yeah. So you see that is the flow rate, yeah, injection in orange. We stop the pump, so the pressure decreases, and that's called the shut-in. This pressure decay is very informative about what's happening in the fracture, yeah. And then we do something that's called a bleed-off. We open the uphole valve very briefly and close it again. And after this opening, I mean, during the opening, the pressure is immediately zero at the surface. But then when you close the valve again, it recovers. Yeah. Why does it recover? Because now the fracture still has some high pressure fluid, and that flows to the interval. Yeah. And it flows on the cost of the aperture change, right? I mean, the fracture closes, yeah, and squeezes out the water back into the interval where we can measure it. And these more like magenta curves give you this production, yeah, how much fluid is produced and per minute, yeah, okay. And here two examples, the one that I showed you before, the 22.4 meter and the 56.5 meter interval. And what we noticed is that this recovery is very different from interval to interval. Here you see that the recovery was almost to the same level as before, pressure-wise, yeah, and it took, yeah, maybe 2 or 3 seconds for the fracture to do so. In this particular interval, it never ever got even close to the pressure value it had before, yeah, and the evolution took much longer. Yeah. Okay, and sparing you all the details of the analytical solution of that differential equation, yeah, the solution models our observations. That are these recovery curves that I just showed you for these two intervals, and all these many colored lines are outcomes of our analytical model, and you see that they are pretty close, right, to what we observe. I think one cannot hope for much better, yeah. And what are the parameters that we determine from that modeling? It's in this contact law, it's the stiffness at the onset of contact, and it's the maximum aperture, if you want to, this K naught and delta naught, yeah. And all these model curves, the red ones are for this fast responding one, and the blue ones are for the slow responding ones. Yeah, these are these points here that plot in the space K naught delta naught. Yeah, and the other two parameters in our model is the length of the fracture away from the borehole and kind of the height of the fracture in axial direction. And since we know that from our fracture traces, that is the range of LF values, yeah, so we could restrict what are the outcomes here, and that's kind of done on this side. So the one that is responding slow, that is short and leaky, fractures leaky, that would be the next parameter, that's the leak off. It has a lot of leak off. What does short mean? It's about a meter long away from the borehole, effectively a meter. You don't have to take this as as precise determinations. And the red one, that is rather long, 10 meter or longer, and it's very tight. It's not losing fluid to its environment. It keeps it. And in terms of stiffness, yeah, we are back to 10 to the 11 or less, but this is not the this is only the stiffness at first contact. So the effective stiffness at some load is higher. Yeah, so it matches again very well with the typical range of stiffnesses that you have. And it seems like there is a stiffness difference by about an order of magnitude between these two types of fractures that have this distinct response. Okay, and the second aspect here of this STIMTEC data is looking at these step rate tests, where we successively increase the flow rate here in green in little steps, and the blue is the pressure, that results from these flow rates. And again here, some examples out of these 10, and they form to us two groups. We do see pressure responses that are more or less constant at reach some constant level, which we call a pressure plateau, or the whole group, the pressure plateau group, at constant injection rate. And then we have the positive tension group, where the pressure does not stop increasing at constant rate. If you talked to a field person doing pumping tests, she would immediately say, this is linear flow, and that is radial flow, and if you have fractures, then this is axial fractures and that is radial fractures, end of story. That would be the conventional interpretation of pressure diffusion. But what we did is we applied this the scheme here that I showed you, this here, the modeling, the coupled modeling for radial fractures to either group. We ignored this common wisdom. We said, okay, we just try to model them both with a radial fracture. So cross this out, we just used radial fractures. The pressure plateau group, which should not be modeled with a radial fracture, actually is nicely fit. These are examples here again, and this is the misfit space, and it has a distinct minimum. So we find the best radial fracture, that nicely matches. Actually, I don't know which one it is now. Probably this one here. Matches nicely every single pressure level. And the parameter space is again length, the radial length, so the radius, if you want to, then the product of kappa and delta, in megapascal, and the initial aperture. So you see the megapascal is 10 to the 6, multiply this by tens of micrometer, then we are again back at 10 to the 11. So that for the kappa, nothing unusual. And the pressure plateau group that would have been expected anyway is also fit well. We have a distinct minimum somewhere here, again in this space, and the curves are nicely matched. Maybe this one is the one with the lowest misfit, probably yes. It's probably hard to tell the difference between this misfit space where it is and the other one. Therefore, I collected that for these 6 tests, 3 in the pressure plateau group and 3 in the positive tension group. And they actually kind of occupy different volumes here in this space, in this space of fracture properties. The positive tension group, they are short. We heard that before. They have a bit of a variable aperture, and they are not so stiff. Very much in line with Jens' work. And the pressure plateau group, they are long, about 10 meters maybe. They are not quite as wide, and they are stiffer. So 2 totally different observations from one test. Totally different protocols here for the pumping. In one, we didn't pump at all. In the other one, we pumped. In the one, the fracture was closing. In the other one, we opened the fracture by increasing the pressure. And they essentially give the same result. And notably, yeah, with two different geometries, so it's fairly robust, yeah, and being able to model that just with a radial fracture also tells you that this common wisdom based on diffusion theory is probably at stake here. Yeah, I mean, it's not necessarily true that when you have constant pressures at constant flow rate that you envision an axial one-dimensional flow. Yeah, and since this is a numerical model, we can look at everything, also at the pressure distribution. So the fluid pressure, here's the interval into the fracture. Yeah, here for one of the very long ones, 50 meter. And you see that the pressure is not constant at all in the fracture. So it's kind of counterintuitive. Yeah, in the borehole, you have constant pressure during the pumping, but in the fracture, it's very non-constant. And the other group where we have a constantly increasing pressure in the borehole, the pressure in the fracture is always constant. It always is almost exactly equilibrated with the pressure in the borehole. And I think these are, coming back to where I started, these findings are extremely important, because a non-constant pressure means that you have to be a bit more advanced in your Coulomb stress analysis that operates with a constant fluid pressure. Yeah, and think about that again. Okay, and in this modeling, we can also nicely separate these two contributions that I talked about very early on: the contact stiffness and the geometrical stiffness. And this is the pressure plateau group, the one with the immediate response, yeah, and that is actually controlled by the contact. The stiffness is controlled by the contacts, while the sluggish one, yeah, in the positive tangent group, they are controlled by the geometrical stiffness, which is actually the lower bound. Yeah, stiffness cannot be below that. I guess that was, what I was afraid it would be too much. Maybe I make up for that in the conclusions. Deformation matters. Yeah, it's not only stress when it comes to hydromechanics. We have to think about expanding our models here. And if you haven't got the notion already that I'm fixed on fracture stiffness, yes, I do think fracture stiffness is important. Yeah, and the trouble, it's a troublemaker at the same time. It causes nonlinearity, yeah, which makes any modeling a challenge, right? In closer detail, what did I show you from the lab study? Contact mechanics, they are nonlinear, yeah. Then do we get, can we determine hydraulic properties of fractures in the lab under in situ conditions? Yes, I think we can get constraints. The global cubic law does not seem to hold well, yeah. And important observation was that you have, during sliding, you have fluid pulses, yeah. And from the field, contact mechanics versus geometrical stiffness, that was kind of my last slide, yeah. First of all, for whatever reason, let's use the numbers we get from the lab for contact mechanics in situ. It seems to work well, yeah. The nonlinearity and coupling gives you an alternative explanation for old observations, old here diffusion-based. And the geometrical stiffness is important whenever you come close to opening of fractures. Otherwise, you can probably safely ignore it. Yeah, and with that, I would like to thank you for your attention.
Great. Thank you very much, Joerg. Everyone, please unmute. Yeah, and join me in thanking you. Yeah, very nice.